time to revisit my Peerberg pump controller, homemade, using an Arduino. And here are my fish that are still resident from last time, not involved in the experiment. And you can even hear my dishwasher running again in the background. Ignore that. So we're going to have another go. And I spent a long time. I'll just show you the circuit. So the circuit itself is unchanged. There's a voltage regulator, there's a bit of an amplifier with a couple of transistors, and then there's the Arduino. An Arduino, for those who don't know, is a microcontroller. So you might consider it to be an extremely cut down PC, I guess. Much lower power than even a Raspberry Pi, let alone a Windows machine. And it is, the programs it runs are held in what's called non-volatile memory. Basically it means once you've programmed it, that's it. It will remember that program forever. And the programs you create for it are done via a system called Arduino IDE. So let me have a look at that for you. Okay, so this is the integrated development environment, and this is the code. I'm not going to go into the whole business of how you write code. There's much more expert people creating YouTube videos than I am, so I'll just breeze past it. So the code is written here. You compile it and you upload it to the Raspberry, and then it runs. And that's it's pretty complicated, to be fair. But from the point of view of this experiment, the important part is I've changed the function of the PWM. Now, thanks to a commenter on my last video, it became apparent that the weakness in my code previously was that I could not set the frequency. As I'll show you a slightly different version of how it was to run this. And this one we have a a library which is called PWM, or pulse width modulation, and you can, with this version, alter the frequency. There it is. So the PWM function is down here. PWM right. And somewhere up here is the frequency, pin frequency safe, I don't know why it's called safe, is 300. And this is a figure you can configure. And it's already different from before. So that's it. I'm not going to go into the code any further than that. But what it does mean is I can do more with the PWM than I could previously. So with my control knob, as before, I can alter, hopefully you can see the waveform on my miniature oscilloscope here. You can see the proportion of up to the proportion of down. So basically that means here is probably about 25% duty cycle, so roughly 25% of the overall pattern is up and most of it is down. Whereas I can change it to be, let's say, 75% duty cycle, so 75% up and 25% down. And that's exactly the sort of thing, that's what PWM is. And that's what we want to control the pump with. It didn't work last time because we discovered that as soon as I changed anything less than 100%, it would switch off, and that's obviously no good. So the question is, what frequency should it be running? Because this is not altering the frequency, this is only altering the proportion of the up and down. So we can, unlike previously, we can now alter the frequency. So it is a bit of a rigmarole, but we can do it. So up here is the figure where we determine the frequency, which is currently set to 300 Hertz. And we're going to change that for demonstration purposes. So let's make that 1000, and then we will compile and upload. So it's compiling now. So you wouldn't want to do this very often, but hopefully there's only one figure which is correct for the pump. Anyway, this is happening in real time, and we can see the little message here saying it's compiling, and then the stage which is causing me a bit of trouble is the uploading stage, and we'll see whether it works or whether it needs to take several goes. Oh, it's done it straight away. How amazing. Now you can see that the pattern is a lot faster, roughly 3 times faster, and yet we can still change the proportion of up to the proportion of down. So this is a much more sophisticated version than we had previously, when it was not possible to alter the frequency. So I'm going to go back to the Arduino IDE. I'm going to change that figure back to 300, which I suspect was the correct one, but we'll find out whether it was or not. Not 3000, 300. So we're going to compile and upload. In fact, I'm going to point you at the screen and see if we can see it. Oh, it's switched off. And now we're back to our slow pattern, or slower pattern. This is the original code, and the completely different function was used. There is, analog write, there it is. So this is the function that was previously using analog write, which produces a PWM square wave, but there's no control over the frequency function. It was about 400 and something hertz. I'll put the correct figure up on the screen. So here we are back to the same. In fact, it looks remarkably similar to what it did a minute ago, but we now have control over frequency. So some considerable time later, I have got the pump. This is not the one that's in the car, clearly, it's on the bench. This is my genuine Pierberg pump that came from some kind of BMW, and I spent a long time getting it to work at all, which is one thing. You can obviously get it together by shorting pins together. So just so you know, there's 4 pins in here, and with the rounded end is actually pin number 1. So you get 12 volt power, then the signal from the pulse generator, then you got ground for the signal, and then power ground. Now, one thing I discovered is that basically it doesn't work if you don't have the 2 grounds connected together. So that's what this lumpy thing here is all about. So the 2 grounds have to be connected together, otherwise it doesn't work. But having said all that, I've now got a control. So this is currently, now it is currently running at 100%, and it's drawing, this is milliamps. So that is 6.7, so 679 milliamps, which is doesn't make any sense. Now it's half an amp. 6.7 milliamps is 0.67 of an amp. So it's taking half an amp, or thereabouts, which I am surprised. I thought it was much more than that. Well, there we go. So real-time discovery, if you like. So in terms of the alternator power budget and how quickly it'll flatten your battery, half an amp is kind of neither here nor there. It's in the meter, by the way, is in series between the bench power supply I'm using and the the rest of it. And if, in fact, if you wiggle the voltage up and down, it's currently running at 11 and a bit amps. I don't know if this thing's switched itself off. Check it's still running. Yeah. So I can increase the voltage to one that you might expect, and the engine's running. So that is 14-ish, no 13-ish. Right, that's basically 14 amps. And as you might have noticed from the noise, the speed of the pump stayed exactly the same. So if I drop it down, it compensates. So it's got some clever brain in here. Anyway, turning up to about 12, and then we have the pulse. So this is currently on 100% duty cycle, so that's why it's just a solid yellow line at the top. If I speed it down, there we go. So it's doing what you would expect. So turn it down to a low figure. Something like 25%. Actually, it says, it's quite good, this scope. It says 29%. Let's turn it down to 25. You probably can't hear it anymore, but 24.8 duty cycle on the pattern here, and it's drawing 200 milliamps. And if I wiggle the power supply, still seems to be doing about the same speed. So take it back up to engine running type voltages, and now we can turn the duty cycle up. Yeah, so and if I switch it off, yeah, it's actually stopped now. I'll turn it on again. Okay, so basically it works in a way that it didn't work last time. Previously, I had to have it on 9 volts, otherwise it wouldn't work. Which is a bit strange. I don't know what's happened to that. Maybe my wiring wasn't good enough or something. I don't know. But this is the new Arduino code doing this pulse thing here. And in fact, I have got the frequency, and I'll bring you up here. The frequency is 100. I've been trying different frequencies. And this is 100 hertz, but I can change that to be 400, for example. Might try a higher frequency as well. So it's compiling that, which actually causes this pump to stop while the thing switches off. And it's obviously still running. Right, yes, so rewind slightly. So I increased the PWM frequency from 100 to 400, and it does look rather as if doesn't make any difference. But I'm going to take it back up to, I think we're going to put it on 400, which means you could have probably used the original code as well, but it doesn't matter. So I'm going to put it on 400. It will reset itself again. 400 because I think the throttle body, which is PWM controlled, runs at 300, so I'm going to make it a different frequency to that. So we're now running 400. So there we are, my genuine Pierberg BMW pump. Seems to be perfectly happy with my Arduino controller this time. And there's no silly business of it needing to run only on 9 volts, so I've no idea really what that's all about. Now clearly the knockoff one, bear in mind that the chassis is not bracketised for this pump. The knockoff one might be different, but it means that I can now experiment with that similarly to this, but I shall obviously have to do it on the car and plug into, it's plugged the same as this one, in order to do the messing around, see if it works. So yeah, PWM on the Pierberg CWA pump seems to work with an Arduino thing that you can make yourself. And just as a nice to have, I've put in, this is a serial monitor, so you can see the Arduino actually tells you what it's doing. So it's telling me what the frequency I've set is, and it shows the value of the variable resistor potentiometer combined with the duty cycle of the output. So if I swivel the knob, as you can see, the figure changes, the frequency doesn't. And it looks like it starts to have an effect on the running speed when it dips below 70%. It goes all the way down to nothing. Of course, the next thing, it's no good having a variable resistor in the car to control the pump speed. It needs to be linked to well, engine temperature. So remains to be seen whether this can be linked to the energy management system, which measures engine temperature, or not. But it is interesting because the ME360 ECU does have some PWM outputs of its own, which would, I suppose, replace all of this. But that's a couple of steps further on. What I would really like is for this to behave like a thermostat, so the water doesn't circulate really until the engine's warmed up. At the moment there is no physical thermostat, so this would be a way of achieving that. Anyway, that's where we are at the moment.